Welcome to a short introduction to powder bed fusion, additive manufacturing technology, specifically one that uses lasers to print with metals. So I want to give a short introduction about the benefits of this technology, what its basic principles are, how it's being used in the industry, and why it's gaining a lot of traction and making a lot of headlines in recent years. So the process chain of laser powder bed fusion is basically, in its principles, the same as in all additive manufacturing technologies. It starts in the digital domain. So at the beginning of the process chain, of course, you have customer requirements, you have part requirements, and then up until the production of the actual part, it's all in the digital realm. So you work with computer-aided design programs, computer-aided engineering, computer-aided manufacturing programs, and do your build job preparation all in the digital domain. So once you have done that, once you have constructed your component with a CAD program, then you can go to a laser powder bed fusion machine and have it printed there. The printing process, usually when it's printing, is an automated process, and then there's still some, especially in industrial context, there's some compulsory post-processes. For example, with the laser powder bed fusion with metals, you usually have to do a heat treatment after printing to get rid of residual stresses that occur during the process. You have to do some surface finishing on some components. You have to get rid of some support structures, or also get rid of the component which is printed on a base plate and stuff like that, and you have to do some quality assurance. So printing is not the last step of the process chain. There is still some compulsory things and also some specific things that you need to do to your components. The laser powder bed fusion process itself can be conceptualized as a welding process, where we have basically a line-by-line and layer-by-layer welding process. What that means is we locally melt the powder with the laser beam. Usually feature sizes range from 50 to 200 micrometers in size. And we locally melt the powder and have it then solidify. And we add each line next to each other, and then we add another layer of powder, and then repeat that process over and over again until we, in that manner, build up a whole component. But the important thing is, if you have experience with welding, then you can already transport a lot of the knowledge of welding into this process, because in its concept, it is a welding process. And if you use this analogy that it's a line-by-line, layer-by-layer welding process, it can help you a lot understanding the main challenges and also the main benefits of the technology a bit better. In the news, you can often see laser powder bed fusion being marketed with the use of various lattice structures, because that is something where the technology can show its benefits most clearly. Because with the technology, as mentioned, you get complexity for free in a way. You can have very complex structures. You can have uniform periodic structures, conformal periodic structures, or even stochastic structures if you have a program that gives you some randomized tooling paths. And with that, you can build very complex lattice structures with the same costing as if you would print a solid block. The specific use case that you can use in an industrial case, where you use these lattice structures for an actual component benefits, could be, and you can also see this in the very first applications which have been marketed in the news a lot, is the use of reinforced beams or reinforced brackets, where you can use also very specific software simulation tools, where you can use topology optimization to have a perfect ratio between the weight of your product and its capability of transporting forces or withstanding pressure or something, whatever you want to simulate with it. And laser powder bed fusion gives you then the opportunity to print this completely digitally fabricated product as it is in the digital domain. And that can save you a lot of weight, that can save on or can increase efficiency for your component, and yeah, has very direct benefits to your specific use case there. A bit more specific, maybe for certain industries, you can also use laser powder bed fusion as a precursor to the serial production of a component, maybe with a different technology. And if you want to use laser powder bed fusion to just quickly in the design phase build a prototype and then have already some critical testing features in your component printed. For example, you can add dampers or you can add channels in your component where you can already then put some sensors in and have it being used in some testing for early prototyping of your component, which can drastically improve development cycles of components. Another thing where laser powder bed fusion is being used for great benefits is the broad term of assembly integration. Usually because of conventional production methodologies or production process steps, you sometimes have assemblies which consist of 10, 30 or up to 100 individual components which have to be assembled in individual process steps. But laser powder bed fusion has a unique ability because of its capability to produce internal structures and to have closed internal surfaces. You can have that whole assembly printed monolithically in one go. Another recent industry that benefits a lot from laser powder bed fusion is any industry using heat exchangers. For example, in the construction or in the energy sector, it's a very important topic right now. And put simply, heat exchangers gain efficiency from their volume to surface ratio. So the more surface you can put in a specific volume, the better your heat transfer mechanisms can operate. And laser powder bed fusion, because of its technological benefits, can help you to have enlarged cooling surfaces within a very tiny volume with a precision that has just not been able with any previous technology. Generally speaking, when you want to use laser powder bed fusion, it's important to have a guiding principle, so to say. And one guiding principle could be to add value to your component. Usually, if you just take a component as it is being produced conventionally, then you will not see a positive business case because it is a very novel technology. Usually, it does not have the monetary benefits that the conventional manufacturing technologies are already using from serial production, from economies of scale or something like that. So with laser powder bed fusion, you need to be aware that if you want to have a positive business case, if you want to use the technology for what it's actually capable of, you need to think about using laser powder bed fusion and adding value with it. So usually there's two main ways you can use for this. And one would be to increase the performance of your component, whatever that performance may be, however you measure that component performance. So that could be you increase the lifing of your component by using simulation software to give you an optimal design of your component. You can reduce resource consumption by reducing the weight of your component, maybe for an aerodynamic standpoint. You can increase the efficiency of your component. You can increase its structural integrity. You can reduce the mass of your component, for example. But it doesn't have to be always a an industrial process indicator. It can also be that you improve the aesthetics of your component, which might be of benefit to you and your business case. On the other side, you can also maybe reduce the costs of the component in a broader sense, maybe by reducing the sourcing of individual companies where you have an assembly, so you can integrate different parts into a component and have a cost benefit not on the individual component itself, but on the broader scale of it. You can maybe reduce also material volume, which will save you costs here. So to summarize, let's start with some limitations of the laser powder bed fusion technology. So what is very important is it can be a limitation, it can also be an opportunity, but the production decisions are very part specific. And that is sometimes a hurdle with this technology, because you can have very similar parts and one works really well for laser powder bed fusion and the other does not, but it's a very specific reason always. And it can be very complicated to figure out which part actually is very much suited for the technology and which one isn't. So that can be a limitation of it. And also getting people to acknowledge that laser powder bed fusion is the right way to go for a specific part can be a hurdle. That also ties in with the next limitation of it. It is a very novel technology. So specific guidelines, design philosophies and expertise are still quite rare. And the technology itself is based around individualization and customization. So due to that, there are limits to scalability. It's not a production methodology where you can have one component printed in the order of 10,000 a year or something. You rarely would do that. You have to use the technology for the specific use case that you have, but you have to be aware that there are limits to the scalability with this technology. And all of that makes the financial evaluations quite complex sometimes, because if you don't really use the technology to its full extent, then it becomes hard to actually make a business case, a positive business case. So when you have those guidelines, when you have the expertise, when you have the design philosophies, and you have a component that can really benefit from laser powder bed fusion, it does make sense. And lastly, let's talk about some opportunities of the technology. So one thing that the technology offers, and that is probably its most attractive advantage, is the improved design space. So one common thing in architecture that maybe can use as a guideline here is the phrase form follows function. So usually with conventional technologies, you think about what tools you have and what you can do with it. But with laser powder bed fusion, you can reverse that. You can think about what functions do I want to have, what problem do I need to solve, and then you can design for that function and then afterwards, well, print it. If you, of course, follow some design rules, that's clear, but you can think about your function first and you don't need to think about so many details about the production methodology restrictions. Another benefit of the technology is the idea of mass customization and easy individualization. Since we print components from the digital domain, we can individualize each component with, let's say, some markings, some codings, or some slightly different design variations. So with conventional technologies, that would require individual programming or individual casting or whatever your production methodology was. With this technology, it doesn't matter that much. You just printed a slightly different design and you can have it. And with that, you can also do some on-demand production. So one of the most attractive things about this technology is if you have a part that you don't need that often, you don't want to store it or have a supplier on hold for whatever time there is. With the with the printing technology, you can just print it at the time that you need it and yeah, take advantage of that. And with the laser powder bed fusion, you have a very efficient product development cycle because you can parallelize the design, the prototyping and the testing during the development of new products or during the improvement of existing products. So while you're already in the design phase, you can print a few early designs and already see if some of those ideas actually work out, so you can print functional components very early in that process and have them put on a test rig and see whether ideas are worthwhile following up on or if new products can be improved. So yeah, that was the summary of laser powder bed fusion, its limitations, opportunities and its basic working principles, and thank you for listening.